To see one of the very interesting problem in combinatorics, which is grid problem. It's not only limited to solving grid questions, but also many questions of functions, as well as the other branch of mathematics, specifically in discrete mathematics. It has wide implications. So let's start by taking a simple layman approach to grid problem. So the problem statement goes like this. We start from the point S, and you have to go to the point E. Now the rule of the game is you can only take either a right step or an up step. So either you can move right or up. So left and down is not allowed, right? So you're not allowed to move left and down. For example, if I start here, you are not allowed to go like this. Okay, this is a wrong path. Why? Because although it was right, up, right, but you came down. Okay, so because of this, it violated the rule of the game. So I have to go from point S to point T, such that always only right and up move is allowed. So in how many ways you can do so? You can just play with this like a class 8 level kid, and let's draw some of the path for this. I'll go right, up, maybe right, then up, and we got this. So this is one of the way of getting there, right? Other way of going there, you can go straight up to the extreme corner and then take right, and that's another way of going, right? We can have so many possibilities. We can go like this. It looks fanciful. Even you can take this path, and so on and so forth. So now the question is, how many ways are there to go from S to E? So clearly you can see the number of steps that you are taking is 1, 2, 3, 4, 5. 5 steps along right direction, and we have 1, 2, 3, 4, 5 steps along up direction. So give it a try. Before you give it a try, you can do a simple counting. So let's say if I start from here, a starting point. At this point, how many ways are to go? There is just only one way, right? Similarly, how many ways are there to go to this point? So at this point, let me give a numbering to number of ways at nodes 1. So if I start at a point, we have one way to go here. From here, we have definitely one way to reach to this point. But I can reach to this point from other path also. Okay, so at this point, we have one way. And now we have 1 and 1. So we have 2 ways to come here, right? Similarly, at this point, we have only one way. Because you can from S to this, there is only one way of going, right? So at every node, I'm assigning a number to this. The significance of number is it represents number of ways to come to that point from the starting point. So 1 represents only one way. This one represents one way is there. This one represents there is only one way to go to this point. It's not 1 plus 1. This 2 represents there are 2 ways. You can clearly see the path. One path here, other path is this, right? What about next guy? See, to reach here, you have 2 ways. Either you can come from this path or this path. This path means you come via this or this. To reach here, now we have one way is this, other way is this. So basically, we have 3 ways of reaching there. Why? Because till here, I have already exhausted 2 ways. So you can go via this one way or this 2 ways. So that 2 is automatically counted while traveling, right? And we have one way there. So from there, we have no ways, 2 plus 1. So that I can assign a number. Let's say 3 to this. What about this point? Already at this point, you have 3 ways. So here also we'll have 3 ways by that track. At this point, we have 1 way. And here we have 1 way. So the only way I can go to this place is straight up and then here, right? So we have 4 ways of going. Now you already know like there is a definite pattern in which we are able to count, because again at this point we have 1 way, we have 4 ways. So total is 4 plus 1, 5 ways of reaching there. A child is counting, right? It's 1 way. And now once you have reached there to this position, how many ways are there to reach here? You don't have a choice, right? So we have 1 way and 1 way. So we have only one choice of reaching from this point to this. But since to reach to this point, I have 5 possibilities, and here we have 1 possibility. So overall, we have 6 possibilities. Meaning, from a starting point, I can go in only one way along that track. But to reach here via this 5 possibilities, we have many possibilities. You can go straight up. Let me use different color, or 2, or 3 or 4 ways or 5 ways. Now you can clearly see the answer on one of the vertices of this square. A small square is nothing but sum of the numbers appearing on diagonal. So we have 1 and 1, hence the answer is 2. We got 2 and 1, and this answer is 3. We have 3 and 1, this answer is 4. 4 and 1 is 5, and 5 and 1 is 6. Now clearly, if you want to find how many ways are to go there, right, we must know how many ways are to come to this point. So again, you can do the enumeration, like basically we can count. So at this point we have 1 ways, right? So we have 1 way of going via this path in 2 ways. So 1 and 2 is 3. Again, we have 3 and 3 is 6. 6 and 4 is 10. 10 and 5 is 15, and so on and so forth. So I hope now you understood the game. So let us just run this a small animation to understand perfectly what I am doing in a neat and clean way before. Okay, so basically, as I was explaining, you see, straight away on the first track there is only 1 way, and every time you are moving, clearly you can see from the animation the number of ways are getting added up. So fundamentally what we are doing is we are doing enumeration of the method. So as you can see on every word is 6 plus 4, so 10 will be the new outcome. Again, you have 10 ways from this side and 5 ways from there, so we have 15 ways of getting there, and so on and so forth. So this is a way like you can run a simple programming, or you can do it mechanically by hand to count the number of ways goes from a particular point to another point. Okay. One very exciting thing, like those of you who have already done binomial theorem, is can you see these coefficients? Don't you feel they are interesting? So you think of the diagonal terms. You imagine the diagonal entries of this matrix format. So you have 1, 1, 1, 1, 2, 1. So the very surprising factor is the number that is written over this node is something really special. This 1, 4, 6, 4, 1. We have 1, 5, and 10, 10, 5, and 1. And you can clearly see like these coefficients appears as if they are the expansion of x plus y whole square. That is x square, 2xy, y square. X plus y whole cube will have coefficient as x cube, which is 1, and 3x square y, 3xy square, and 1. So these elements, the numbers which is written over this diagonal element, is surprisingly has some connection with x plus y to the power n. So it means if I make this grid instead of 5 by 5, if I make it, let's say, n by n, you can directly find the formula for x plus y to the power, let's say, 10 by just looking at the nodes. And that's the beauty of mathematics. Like, you never learn mathematics in compartments. It's an integrated idea, an integrated philosophy as a subject. Having understood this, and also the link is like it has to do something with binomial theorem, hence binomial coefficient like NCR, N choose R, or something. Let's try to directly hit hard on this head and see if we can directly give the answer without this child discounting. And here we go. So before we again try to understand this answer from a different perspective, the one way of analyzing this is, let's consider any path. So since I have already drawn the diagram, so I'll redo it for one of them. So let's say one of the successful or the valid path from S to E. Let me draw one more and one more. It's always nice to play with the questions by taking a smaller cases. And now what I'll do is very smartly I'll try to decode it. What I mean to decode. You see, I'll try to convert this question parallelly into a simpler question, which in a mathematical language is known as bijection. So bijection is basically you convert this problem into a smaller problem which is easy to comprehend and easy to solve. And then you are like number of counting, number of objects in the first problem is same as number of objects in second problem. This is quite fundamental to us since childhood, because when you are doing counting 1, 2, 3, 4, fundamentally we are already creating the image of some object in our brain unconsciously. And then we are calibrating those images with the object which is available, and hence we count those numbers. So even the very fundamental idea of counting is basically a bijection which is embedded in us since childhood, but because of less mathematical consciousness we are not able to comprehend it. Like, it's basically mathematics without knowing it, right? Anyway, so let's go ahead. And what is common between all paths? See, a general art of problem solving is finding commonness between uncommon things. So I know like all these parts start from point S and they ends with E. What else is common between them? Apart from they are like crazily going from this. Now one of the common thing for a class 4 kid will be, okay, all these parts are embedded within those square or maybe sandwiched within the square. So is there anything like which is more strongly common between them? Well, they are moving on a grid and you are only allowed to move right and up. Apart from that, give a trial. Yeah, so here we go. What we can see, like in any path, the number of moves, the total number of moves in the right direction is constant. For example, for the first part, we have moved one right, then we have moved up, again then right, up, right, and only up, up, up. So how many moves are there in right direction? Clearly you can see 1, 2, 3, 4, 5. So we have 5 moves in right direction and 5 moves in up direction, right? It will always be the case for everything, and this is basically known as projection in your physics, right? Because to move from S to E in any path is fundamentally taking 5 steps along right and 5 steps along up, no matter what part you choose. So let's say this red guy, 1, 2, 3 up. We have again right, up, right, up, right, right, right. So again, if you see the red guys will have 3 up plus 2 up, which is 3 plus 2, which gives you 5 up, and we have 5 right. What about the other guy? Let's count again. We have right, up, right, up, right, up, right, up, right, up. So we still have 5 right and 5 up. Oh, so far so nice, so good. Because even if I now pick up some other guy, if I'm gonna pick up some other guy, still you can convince yourself very easily. Like you have to lift yourself by 5 units in the up direction and 5 units in the right direction. Okay, so any path can be resolved into 2 fundamental basic directions, right? One along right and one along up. What's great in that? The greatness of this is now we can decode any of the paths. So let's say if I can decode the path, what does it mean to decode it? So let's consider the first path that I have drawn, and let's write the sequence of activities that we have done. So we have right, and up, right, up, 5. So we have 5 rights and 5 up. Mass conservation. What about red guys? Let's decode this path now. Let's write it in a sequence. Up, right, up, right, up, right. Okay, so you can count, we have 5 rights and 5 ups. One more. Right, up, right, up, right, up, right, up, right, up. So we have got again 5 up and 5 right. And you can, the list continues, you can write as many as, in fact, the answer. Yeah. Anyway, so what can you see something common in this? Basically, you see we have a string of 10 objects here, string of 10 letters, which contains 5 right and 5 up. And in how many ways you can arrange this? Because you see, what is counted in this string and this string? It's basically same 5 right and 5 up together, but the arrangement is different now, right? Arrangement is different now. And every possible arrangement, let's say someone blindly writes right, 5 right and 5 up together. And you keep on writing any random arrangement in a row of 5 right and 5 up. Corresponding to this, we'll always have a path here, right? Why? Because you can back decode it or do reverse engineering. So how many rights are there? How many rights are there? Okay, we have full right and duty also to solve this. So we have 5 rights. So 1, 2, 3, 4, 5. So these 5 rights represents You're going to extreme right corner, and 5 up means going directly up. So you see, corresponding to any permutation of this string, there will always be a unique path associated with this. So how many such strings will be there? It is same as the number of paths. So the question is, how many such paths will be there? So the question is, how many such paths will be there? Clearly, the number of paths will be same as number of ways in which these 10 letters can be arranged among themselves, because every arrangement is having a unique contribution to the path here. And now it's very easy to count, because if all these letters would have been different, you can arrange in 10 factorial ways. So assuming you already know the basic PNC. Now since 5 of them can internally dance in 5 factorial ways, so we have to divide it, because even if they are different, that is also counted in 10 factorial. Okay, so even if R1, R2, R3, R4, R5, they are internally changing their position, fundamentally we have just one arrangement. Hence you divide by 5 factorial to lower down the number of cases. And same thing goes for up, which is a very standard thing which you have done since childhood. And that solves the question, because you see clearly the answer is 10 factorial by 5 factorial by 5 factorial. In a cool way, this is known as 10 choose 5, because out of 10 objects, you are choosing 5 objects. This is a definition of that. It can also be written as 5. So hence the answer for this problem in animation that you are seeing, like for 5 by 5 grid, the answer is nothing but 10C5. Right? So this was one of the very, beautiful application of combinatorics, and an assignment is there for you. In fact, this idea can help you to get the answer for a number of non-decreasing function. You can in fact devise a bijection between number of non-decreasing function and this grid problem. I'll come with one of the interesting concept of Catalan number in the very next video, and which will come soon, where you have to move from point S to E in such a way that you are not allowed to move above the diagonal. So let me pause the question. So now here is an assignment for you. You have to move from point S to E in such a way that you are not allowed to move or allowed to cut this line of control. So you are not allowed to move above this diagonal or below this diagonal. So let's say you are not allowed to move in this region. Okay, so this is not allowed. This region is not allowed. Then in how many ways you can do? Maybe some of you can guess like it will be actually half of the answer. Think why. You are absolutely wrong. Because if I start from here, now I'm allowed to touch the diagonal, but you are not allowed to cut the diagonal. Okay, so there will be other way, again third way, fourth way, fifth way, and so on and so forth. So let me draw some more path. It feels so nice to draw it like a kid. Okay, so now the question is the number of ways in which you are not allowed to trespass this diagonal. You are allowed to touch, or you can completely miss it and go out. So give it a try. It will be very interesting. One way in which you can do so in a very childish way is draw this lot of grids the way I have done, and then simply count it for maybe 2 by 2, then 3 by 3, then 4 by 4, then 5 by 5, and try to sense the pattern. Once you got the pattern, try to decode it, hit hard on it, head directly with the combinatorics ideas. Okay, so we'll meet with this video in a very next lecture. Until that time, enjoy the problems.